Hello, my name is Karl, and today I will present some promising initial research completed with Freedman and with the help of the Edge Computing Lab at the University of California, Irvine. We've called it You've Got a Friend in Me, Blockchain Processing with a Cloud Node Backup. So let's jump right in. Many modern computing applications require a large amount of intensive computation in tandem with a rapid response time. Facilitating both of these requirements simultaneously often presupposes access to state-of-the-art hardware, which isn't feasible for many. Thus, many are left with an obstacle, namely that high computational cost implies high latency. Contemporary cloud computing, on the other hand, has sought to bridge this disparity by giving users access to vast amounts of computing power that they normally wouldn't have access to. However, this still comes with its own problems, like sitting behind a paywall, higher than desired latency, and outages or performance variability due to geographic location of the client server. In response to this, multi-stage transactions attempt to bridge the gap between computational cost and latency by performing a kind of load balancing between cloud nodes and edge devices, leaving expensive computations to the cloud and others to the network edge. Where the friend in mobile edge, or FIME, system breaks new ground is in the entities chosen to carry out the cheap and expensive tasks. Specifically, FIME replaces the cloud nodes in the multi-stage transaction architecture with the blockchain. But most importantly, it exchanges the roles of the late cloud nodes and the edge devices. FIME is a developing system, and our results here, I believe, show some promise in the introduction of the blockchain to a variety of interesting edge computing applications. So let's dive into the FIME system, applied to the use case of our prototype of stock prediction. It consists of three components: a client program, an on-chain node in the form of an Ethereum smart contract, but note that there was no reason to use Ethereum over any other blockchain. Merely the fact that it had a bulk of community support was the motivating interest. And this on-chain node performs cheap tasks. In this case, it performs a simple averaging calculation to predict stock prices some arbitrary number of days in the future, capped at 30. The third entity is an off-chain edge node that performs more expensive tasks. In our particular prototype case, it performs a pre-chained long short-term memory machine learning model calculation so as to make more robust predictions. Now, with the goal of providing a low latency response to the client while verifying the validity of the response asynchronously, we will drive through the route a client request in the FIME system takes to achieve that goal. Steps 1 through 3. So first, the client sends a request to the smart contract on the on-chain node, in the form of a tuple holding the stock ticker string and a number of days in the future. So, string, days. After receiving the request, the on-chain node immediately checks its cache to see if the same tuple has been recently requested. If so, it immediately returns the contents of the cache hit to the client in the form of a price prediction. If not, the smart contract is called upon to perform an exponential moving average calculation on its stored data. And its stored data is a subset of the training data given to the LSTM model. When complete, it updates the cache with the key value pair consisting of the tuple and the prediction respectively, marks it as unverified, i.e. unverified by the edge node, and forwards the response to the client. Meanwhile, in step 3 prime, the edge node is going to asynchronously poll the cache of the smart contract for the addition of new stock day tuples that haven't been marked as verified by the edge node. If an entry exists that is new to the edge node, then the smart contract replies to the edge query with the relevant unverified query, where it is received and stored in the edge node. Now, the edge node gets to do the majority of its computation. In step 6, the edge node can independently run the unverified entry through its model Update the lower confidence prediction stored locally and made by the on-chain node with a prediction which can have some higher confidence by virtue of the fact that it's performing a calculation given more training data. Next, the edge node again asynchronously calls upon the on-chain node to update the relevant entry in its cache with a verified prediction and mark it as such. Finally, the client is notified of this change in the form of an apology and an updated prediction. We ran several experiments to generally validate the FIME system and evaluate its performance. Two of the most important I include here. All of the experiments were run with a simulated client launching requests for stock predictions of a random number of days in the future capped at 30. Furthermore, all experiments were run on the same local laptop machine, so benchmarks like the ones depicted in the left-hand histogram illustrate the time required to ingest and compute data rather than the time taken to communicate between entities, by virtue of the fact that they were all run as different processes on the same machine. The right-hand graph supports the results shown in the benchmarks in the left-hand histogram by virtue of the fact that you can see the LSTM model able to adapt to the varying number of days in the future, while the more primitive EMA model run by the smart contract remained constant as expected. You can see this support by virtue of the fact that the benchmarks are stratified into three groups. The first in red allotting 100% confidence to the EMA prediction of the smart contract, precludes any verification by the edge node due to the 100% confidence. As you can see, it has the lowest response time in this case meaning computation time, because very little had to be done. There was no computation or communication and computation done between the edge node, the smart contract, and the client, just smart contract and client. The second in green, giving equal confidence to the smart contracts and the edge node's predictions, yielded double the number of necessary corrections and thus doubled the time taken to communicate between the client on-chain node and off-chain node. And finally, the third in blue individually utilized the edge node, exclusively utilized the edge node, and paid the price and time due to the expensive computational latency. We posit that FIME demonstrates a promising first step in the application of blockchain to edge computing. However, our research has taught us that applications that require the smart contract to ingest, store, and compute on even small quantities of data continue to pose serious financial and latency issues within the FIME system. To this end, we suggest that the on-chain node in the FIME system be used primarily for its greatest strength, that of being an immutable cache of results, and tailor the applications to that quality. Thanks for listening to our presentation about the friend in mobile edge, blockchain processing with a cloud node backup. We now have, I think, 5 minutes for questions. Feel free to ask whatever you would like.